I'm Ruth Hamilton, a clinical scientist working at the Royal Hospital for Children in Glasgow in the UK. And in this video, you'll see me testing my colleague, Bruce Hudson, who's acting as a patient for demonstration purposes. We're going to show you how the diagnosis STEP VEP system works, a system developed by myself and colleagues here at the Children's Hospital. So you can see that Bruce has 3 electrodes across his occiput, a frontal reference electrode, and a virtual ground on his left mastoid. That gives us 3 VEP channels, and we create a 4th Laplacian channel by using the average voltage at O1 and O2 as a reference for OZ. Laplacian channels are good for small signal conditions. The stimulus is a high contrast checkerboard, reversing about 8 times per second. So these are steady state VEPs, not transient VEPs. The STEP VEP software is analysing the EEG in real time. If it finds a significant VEP, it responds by stepping down to a smaller check size, and if it fails to find a VEP, it responds by stepping up to a bigger check size. And we use a 4 down, 2 up, 1 down staircase. I have very little to do here because the process is fully automated and Bruce is behaving as a very compliant patient. But of course, in a real patient situation, I would be constantly observing the patient's fixation and pausing the data analysis for every instant the patient is not looking at the stimulus. In paediatrics, one tester is usually working hard to maintain the child's interest in the stimulus screen, while another pauses whenever fixation is lost. That, of course, is no different to any other VEP recording. Now let's have a look at a couple of examples where we can watch the operator screen in detail. And we're also showing the stimulus screen in the lower right corner, so you can see how the real-time analysis governs the stimulus check size. Now let's orientate ourselves here. We have 4 VEP channels, OZ, O1 and O2, each reference to FZ, and in the bottom right, our Laplacian channel. On the right-hand side of the screen, we have our list of available check sizes, from very big checks, up here at the top, to very small checks at the bottom. So let's start our recording now. You can see the 4 channels of ongoing EEG data. And inset in each of these time-based windows is a frequency-based plot. We're looking for a significant VEP at the stimulation frequency. A VEP was found there, and you can see that the stimulus has changed to a smaller check size. And in the results table, we have a green detection against that last check size, and we've dropped 4 steps, and we're now trying the check sizes indicated by the blue band. If the VEP is quite big and fixation is good, the VEP can be detected in 1 or 2 seconds, so it can be pretty quick. The detection statistics have been designed to keep the overall false positive rate at about 5%. We flag check sizes in orange where the VEP was close to being statistically significant, but they are nonetheless treated as a no, as a red check size by the algorithm. So the test continues, stepping down in 4 here. And for each check size, we have a maximum of 11 epochs before the algorithm will give up and assume that no VEP is present. This is a configurable option, and it depends on the choice of epoch duration. Here, we're demonstrating epochs which are 2 seconds in duration and use a maximum of 11 epochs per check size. There we have an amber result. Same as a red as far as the algorithm is concerned, i.e. no VEP is present, but with a close to statistically significant result, as we already talked about. We will therefore jump up 2 steps. No VEP detected there, hence red. So the test is complete now. Looking at the table on the right-hand panel, you can see that in a downward direction we have green, green, red results for consecutive check sizes, and that is how a threshold is defined. This is analogous to a similar threshold finding technique used in auditory electrophysiology. And let's take a look at how this test would be reported. Check sizes are big on the left through to small on the right-hand side of this central chart, and the grey vertical zone represents normal for age from reference data. Green dots indicate a VEP was detected, red means not detected, and amber means only approach statistical detection level. And the numerical values here give the threshold and precision estimate in cycles per degree, as well as aged match reference limits. And there is also a conversion derived empirically for what the corresponding chart acuity might be. Let's watch another example. A few things to notice here. The process always begins with large checks because we designed the system to maximise the amount of time a child was looking at a stimulus which they could see. Notice also the low noise level on the Laplacian channel. Those close reference electrodes are very effective at cancelling noise, but preserve a lot of the signal. So often the Laplacian has better signal-to-noise ratio than the real channels. We're performing two different analyses on each channel. Firstly, seeking a critical signal-to-noise ratio, and secondly, undertaking circular t-squared tests, which look for vector clusters which exclude the origin. No VEP was detected there, so it's 2 steps back up the staircase. Remember, we're seeking green, green, red for consecutive check sizes getting smaller. That's now achieved, so the test is finished. That one took just 90 seconds total recording time because not too many check sizes were needed. And the report for that test shows the threshold here in cycles per degree, which is substantially poorer than is normal for age. Expressing these thresholds in cycles per degree relative to age match reference data is really all that's needed. There is also the option for the far more variable interpretation as a related chart-based acuity.